Hello, my name is Jack Van Welzen, and I will be discussing the use of advanced correlation algorithms for detecting the crash sites of two lunar landers and how the methods used can be extended to detecting invisible damage in composite materials. Because they are lightweight, yet strong, composite materials are quite common in the aerospace industry. Unfortunately, small impacts, which are somewhat common with aircrafts, can cause damage that is nearly invisible to the naked eye. This damage, called barely visible impact damage, or BVID, can result in serious damage in the composite structure while being very difficult to detect. Current methods for detection are expensive and time-consuming, so a method is proposed here for rapid detection which can be used in routine inspection. This slide shows some examples of impacts and the resulting damage. In the top left, there is an image of a composite plate with a crack that is near invisible. The bottom right of this image shows the crack along with a different method used to detect it. The possibility for impacts comes from sources such as ground debris, birds, adverse weather, or accidents with ground equipment, as demonstrated here. In the case of hail impacts, the damage is visible, but for the others, it is often not. Before applying the technique to composites, the proposed technique was demonstrated on an easier example with lunar lander crash images. The Beersheet and Vikram lunar landers, created by Israel Aerospace Industries and the Indian Space Research Organization respectively, crashed onto the surface of the Moon in 2019. Images from before and after the crashes are shown here. The Beersheet crash site on the left is much easier to see than the Vikram on the right. By running the same similarity algorithms developed for the composite damage detection to locate these crash sites, their effectiveness can be demonstrated. Here, I will play a short video from space.com to give some more background on the Beersheet crash. Here, the algorithms have been run on the Beersheet before and after images shown below to locate the damage. Note that one simple algorithm, called mean squared error, or MSE, is used alongside two advanced algorithms, normalized cross correlation, or NCC, and structural similarity, or SSIM. For SSIM, there are several variations, 4 of which are shown here. While the crash site is somewhat visible in the original images, these heat maps make it very clear where the crash occurred. The same algorithms were run on the before and after images of the Vikram crash, giving the heat maps on the right. In this case, all 6 algorithms are not as universally effective. Mean squared error is able to locate the crash, but also shows evidence of a crash that never happened in the top right. Most effective is the third variation of structural similarity. With this variation, the crash site can be seen without any false alarms popping up. So what's the next step? Returning to the application of damage detection in composites, these same algorithms can be applied. This can be tested on the sample composite panel as shown in the top right. However, simply capturing the images before and after impact is difficult and will likely not reveal the damage like the crash sites were revealed. As such, lasers can be used to gather more information from the panel. Using normalized cross-correlation and structural similarity, heat maps like those in the bottom right can be produced to detect damage. Hopefully, this technique can be extended to rapidly scan much larger areas, potentially including entire aircrafts. Thank you.